Okay, so then we will dive into C. And if you're gonna, so C is a sort of standard language when it comes to implementing embedded controllers. So if you go out to Volvo, there is a lot of C programs there. So it makes a lot of sense to have some basic knowledge of C. I mean, you will not be C experts in this course. That's a course on its own. But at least you will get some, have seen it, and you will get the basic ideas, I hope. And with the virtual computer you have, so the Linux computer, you can very easily start to program your own C programs. And we will also be able to emulate the free RTOS operating system that you have on the Crazyflie, but run it as the whole operating system as a special process on top of Linux, so which is really useful for getting started. So you can just start by open a text editor and create some file and end it with .c. And you might have different preferences for text editors, but a user-friendly one is gedit, so you can install it by running that command. And then you write the program. So here is a very small program, so the Hello World program. We'll come back to the structure of that. But what you need to do is to compile this program to something that the computer understands. And that you do with executing a compiler. And on C, on Linux, a common compiler is called GCC. And then basically you have some parameters or arguments here, and then you write the program you would like to compile, the file name of that, .c, and then -o, and then what the final program should be. If you leave this out, it will be called a.out by default. So, but it's a good habit, I think, to give it a more user-friendly name. And then you have some other arguments here, -w, so that means, or w, all, so that then you enable all the warnings that the compiler can get, so it can be good, especially if you're inexperienced, to catch mistakes that are easy to do with C. And then -g here means that you include all the debugging information as well. That might be good if you would like to debug your program. And yeah, so when compile it here, there might be warnings or errors, and then you might have to go back in the text editor, change it, and recompile it again. But if everything works out without any problems, you will get a binary file that you can then execute. So on Linux, if you just write the program name by itself, it will not find it, because the current directory is not by default in the path. So it will not search for programs in the current directory. So you need to specify /, meaning that in the current directory, look for this file. So this is something you just have to get used to. So, but if you're in the directory where this binary file is located, then you execute it by /, and the file name. And then in this case, it will print out hello world. So if you look at this small example, we can see a couple of things here. First of all, you can have comments. That is /*. So you start the comment like with this, and then you end it with */. So you can have comments that span over multiple lines, for example, possible. So this is just not considered by the compiler at all. And then there is something else. So we have this, what's the English Hashtag, yeah. Hashtag include. And then stio.h. So that means that the compiler will then take what is defined in this file, which are some common functions in this case for standardized I/O. So for example, this printf function is defined inside here. So after you have included this, you can call printf, and then you can print out on the standard out on the console. Okay. So then we see that there is a function here. So it's called main, and it will return an integer, and it has two arguments. The first is an integer, so it's called argc, and the second one is a pointer to a vector of arguments. So we'll come back to what this means. We'll discuss these stars here in more detail later. But this is useful if you would like to send arguments to your program. So, yeah, some size of something, or a text file or a path or something like that, and then you can write it after the program name when you execute it, and then you can read it inside by looking into these arguments here. So this is the number of arguments you get, and these are here. You have this vector that you can read the individual arguments. But we will not go more into these here, because typically you don't use this when you have embedded systems. So first of all, we will print out hello world, and then \n. So hello world, I think it's obvious what it means, but what does \n mean? So this is C notation, so it just means that you should write out the new line. So a return. So it will, if you write something else here, if you write something else, it will be on a new line. If you don't include that, it will be written immediately after the D character here. Okay, and then it will return 0. We mentioned that this was a function that returned something, and in this case 0 is usually used to denote that everything was fine here. So we just return, and we can, if we write something else, we can encode here what went wrong with the program. So there is a way from the shell where you started this program to see what went wrong. Okay. So, and please interrupt me if you have questions here or would like to discuss something. When you compile this, what will happen? There are in C, there are actually two different parts. There is something called the pre-processing part, and there is the compiling part. So, and the preprocessor is a separate program, at least conceptually, that will go and try to read these macros, for example. So it will go and read what is inside this file here and put into the file that will actually be sent to the real compiler. It will also get rid of, for example, the comments here, because those are not important for the compiler, so we'll just throw them out. So we have include files, we have define, we'll come back to these. You can have comments. You can also write, if you have comments on the single line, you can write that as a double slash. So everything else until the end of line will then be considered a comment. So you don't need to end the comment explicitly as you do here with the */. Okay, so after the pre-processing phase, everything is sent to the real compiler that is then turning it into some binary code that the processor can can execute. Okay, so we talked about the function here. So function is a series of instructions to run, and you pass in arguments and you return a value. And the main function is a very special function, because when the program starts to run, the operating system will look up the address of where this function is located in the memory and set the program counter to that address and starts to execute from here. And in this case, so these are the function arguments, as I mentioned, and printf to print out here is just another function that you call from this main function that then has code for actually printing out something on the screen. And then you return the value with the keyword return here. And then you're done with the function. Okay, what else? We started to talk about the memory last time. So how can we think about the memory? Yeah, one way to do it is just to think about it as a big table here with different addresses, and then you can have different values inside each address here. And basically this array can contain 1 byte at every location. And for example then, if you need to store a string, for example, it will span several different bytes here in memory. So something you need to know about C is that if you store a string like that, strings are always terminated by the byte 0. So that's how you, in C, how you know that you're at the end of the string, because then you will find the byte exactly with only 0 or no bits that are set. So in this case you have 5 characters, and then you have the new line character, and then you have the final 0 value. So inside memory you will actually need to use 7 bytes to store this string. So not only 5 or 6 that you might expect. And when you create variables, they will have a certain type, right? And the type, we talked about integers, we talked with and without signs last time. 2 complement method were used to represent negative numbers, for example. So for the compiler, it's important to know when you declare a variable what type it is. So because how many bits do I need to allocate here to store the value? We talked about characters, so they store a single character, so 8 bits will be used here. But if you would like to store a string, we will have a character or a character array. So this is how we say that we have here a character with, or a 10 character array, like that, right? And then we have integers. And integers are, in C, this is a little bit tricky, because if you write an integer, then it depends on the computer architecture, if this will be 8, 16, 32, or 64 bits. So you don't really know. Depends on if it's an 8-bit processor, or a 16-bit, or a 32-bit, or 64-bit processor. So that's why you can take a program from compiled, exactly the same code compiled on one processor, will then have a different behavior than if you compile it on some other processor, because if you, for example, you can store numbers of different sizes. And then we had floats. So this is floating point numbers that we also discussed last time. So they can be typically float is 4 bytes, and then there is something else called double, which is 8 bytes. So we talked about the IEEE standard, and they comes in 2 versions, so the 32-bit and 64-bit version. And then integers, we also mentioned that they can be signed or unsigned, and then there will be different interpretation of the different bits inside the integer, depending on if it's a signed or unsigned integer. So by default, an integer is signed. But if you would like to have an unsigned integer, then you write unsigned int. So unsigned space int. And then there will be a different interpretation of the bits inside the 4 bytes that, or if 4 bytes, yeah. Different interpretation of the bits in the variable. Okay, but I also mentioned that there are int can be 32 or 64-bit depending on the architecture, and that is a problem. So now there is something, if you know that you would like to have a 64-bit integer, then you can include this int types, and then this will be defined for you. So this will be a 64-bit signed integer, and then if you would like to have a 64-bit unsigned integer, you put a u before I here. And then they comes in different versions, so there are 32 and 16, etc. Okay. Okay, so if you declare the variable x here to be character, having 8 bits, then if you don't say anything, the compiler will put it at some address here. But if you don't initialize it to something, it will just be stored at some memory location. And at that memory location, there could be it could have been used for other purposes previously. So there might be some previous value stored here, or if you interpret the bits, they will be. So it will not change the bits at this location. So if you would like to initialize the bits to something, you have to write it to something like this. So in this case, if you would like to initialize the character or y to the character e, so e will then have a special encoding, and then, yeah, the compiler will set it to, in this case, 101 here. So be aware of that. If you would like, you can't declare an integer variable and then assume it will be initialized to 0. You have to set it explicitly to 0 if you want that behavior. Okay. Yeah, I think we talked about that. You need to be a little bit careful with what variables names that are allocated, but or that are legal. But if you use standard A to Z and numbers after a character, you will be fine. So it's usually not a problem. We also talked about last time about different representations of integers. So, for example, if you would like to initialize some variable here, and you would like to use hexadecimal notation, you write 0x, and then you can write from 0 to f here. And then it will be interpreted as a hexadecimal number. So this is also something you can quite often see in C when you read the programs. Something else that you need to be aware of is the scoping of variables. So when a variable is declared, it will only be valid within the scope. And what does it mean? Well, what does we mean by a scope then? So this is a quite illustrative example here. So we see we have a function is declared here, p, and it has some argument x and some variables y and z. And then we have some other variable said that is declared outside the function, so this will be a global variable. We have another function here. So I think we go start from up here and then we go downwards and see what are the variables in scope. So meaning variables in scope are the variables that we can refer to. Yeah, actually here's one thing we can. So this was a function p that had an argument x of type character, and it returned something called void. So that means that it didn't return anything. If you don't want to return something from a function, we just declare the return type to be void. Okay. So when we are here in the program, so the first line in the program, then we can refer to the function p. So p is now in the scope. It's okay to call the function again, for example, because now the compiler knows about that there is a function called p. We can also refer to x. So we can read x, or we can write to x, something like that. It's okay. But before variable y is declared, we can't refer to y here, because if we try to set y is equal to 5 something, or something like that, the compiler will complain. Because y is not in the scope. So it's not a variable that the compiler knows about at this point. But now it knows about it, because now it has been declared. Okay, so at this point here we can refer to p, x, and y. And then we declare another variable, and now we can refer to p, x, y, and z. Okay, so this is the start of the function. This is the end of the function. And if we are down here, we are now outside the function again. So now we can refer to p, because the function was defined before. So p is still in the scope. Here we can call p here, for example. But we can't refer to the variable y and z, because they were local variables within the function. So they are within the scope of the function, and they can't be seen outside. Okay, and then we have the variable z now. So z is in this case a global variable. So now here we can refer to the function p, and we can refer to z. And then comes another function here called q that takes a as an argument. So before this, here we can refer to p, z, and q, and a. And after b has been declared, we have p, z, q, a, and b. Okay, so now something, maybe something funny happens here. Because now you had a curly brace here again, and what you do with these curly braces is to declare a new local scope here. So this variable now is, you can refer to that before you have the end of the scope. So here you can refer to c, but after the end of the scope you can't refer to c any longer. So it's outside the scope. Exactly, and then comes c as before, and down here you can refer to all these, and d, but you can't refer to c as written here. Okay, and then after the function, so this is the end of the function, and then you have the two functions you can refer to plus the global variable z down here. Okay, so this is something to that is important to understand, that you have the concept of variables, and the variables are always defined within a scope. And what you usually need to worry about is things like this, that you have variables are declared within a function. Okay? Questions about the scope? Okay, so then when you write, you will do calculations here, you will implement your control algorithms, and then you will multiply vectors with each other. So you will iterate over vectors, and then you will do addition and multiplication and similar things. So one thing you need to make sure that you don't, or that you have some awareness of is the precedence constraints when you do write expressions like this. So 1 plus 2 times 2 could be interpreted as 1 plus 2 multiplied by 2, or 1 plus 2 multiplied by 2. So you do the multiplication first. And this is defined in the language in which how this will be interpreted. And in this case, this will bind tighter than plus. So multiplication binds tighter than plus. So it will do multiplication first and then the addition. And if you would like some other behavior, then you add parentheses around it. So if you would like this, you write it like that. So this should not be too different from what you've done before. Yeah, and then you can have variables like that. Yeah, and then you can do comparisons. For example, you can compare variables with constants or variables with other variables, like this. Something that could be a problem is how this is interpreted. So here you have a logical OR. So either if this is true or that is true, the combined expression will be true. But how this will be executed in a certain way. So if this is false, oh, sorry, yeah. Okay, we take this example. So if this is true, since this is a logical OR, this will be true no matter what the value will be here, right? So then the C compiler will do something. So it will never evaluate this. And this will only be a problem, or might not be a problem. But if you do something here, you could, for example, call a function that will change the state of the program. Then, if this was true, then this function will not be called at all. So it's usually not a problem, but there are situations where these things matter. And of course, if you have a logical AND here and this was false, instead it doesn't matter to evaluate. You don't need to evaluate the second argument anyway, because it will be false no matter what. Okay. Equal, you have double equal signs to denote. If you would like, the assignment is modeled by just one equal sign, and this is a very common problem. So be really careful when you do assignment, one equal sign, and if you do comparison, it should be two equal signs. And then you have less than and greater than and similar things. So and is then two ampersands, and then you have logical OR are two bars, and then you have the exclamation mark as the logical not. Yeah, you can also do bitwise operations here. So, for example, if you have just one ampersand and not two, as the logical AND meant, then you would do. So if you have two variables that you do, take this AND or bitwise AND between. So then it will go for every pair of bits, it will do the logical AND. So for example, if you take bitwise AND between 1 and 2, so 1 is like that and 2 is like that. So if you take the logical AND, so it will 1 and 0 will be 0, 0 and 1 will be 1. So it will be interpreted as 0. But if you instead interpret this as number and you do the logical AND, so 0 will mean false and everything else will be interpreted as true. So in this case, if you have 1 and logical AND 2, it will be interpreted as true instead. So it will be different. So it matters if you do logical expressions or you do bitwise expressions. You can also shift the bit fields to the left or to the right, an arbitrary number of steps. Okay. So something else. There are some. We talked about this. So this is the assignment operation. So x is assigned the value of y. And let's say x is an integer, then you can increase the value by 1 by writing plus plus. So this is equal to x is equal to x plus 1. Right? So, but you can write it in this shorter form. And then there are two possible interpretations here. So you can, or two possible notations. You can write x plus plus or plus plus x. And they will actually be different, as we see from this example here. So if x is 5 and y is another variable, and you let y is equal to plus plus x, then it will increase the value of x before it does the assignment. So in this case, x was 5, so first it will increase it to 6, and then it will assign 6 to the variable y. But if you instead wrote x plus plus is equal, or y is equal to x plus plus, it will first do the assignment and then increase x. So in this case, y will be 5 and x will be 6 after here. And as I mentioned, you also need to worry about or be aware of the difference between assigning something, one equality sign, or doing a comparison. So if x is 5 and then you compare x to 6, that will obviously be false, right? So then you will not execute this and you will go down here and x will still be 5. But if you make the mistake and try to do a comparison with a single equality sign here, then this will be interpreted as an assignment. So what it will do is that it will assign 6 to the variable x. And this will be a successful operation, so it will go in here and execute the code here. And x will have the value 6, which is probably not what you wanted. So this is a common mistake, especially if you're a beginner with C. But if you have programmed in Java, for example, you've seen this before. Okay. If we now do a little bit more we will go into write some larger programs here, but first we will introduce the if statement. So if you have if, and then you have the parenthesis here, and inside the parenthesis, or between the left and right parenthesis, you write some expression, and then you have the curly braces here to declare a new scope, and then you execute this if this expression was evaluated to true. Else you do what's between these curly braces here. And strictly you don't need the curly braces, you can do without them, but then it will only execute one line after. So usually I always write curly braces, so because if you remove or add lines, then it will be easier to read and you will not make so many mistakes. There is also something you can see in some C programs. There is a short form. So it will X, and then you will have a question mark, Y colon Z. So this will, so it will evaluate X, and then if X was true, it will execute the expression Y, or it will execute the expression Z. So this is just a short form of writing if X, then Y or Z down here. So I don't recommend to write in this form, but you can see it in some code, so it can be good to know what it means. And how many of you have heard about recursion before? So it's about half of you, yeah? So recursion is something that is really useful and fun, but also you can write really nice programs by using recursion. And recursion is not really something strange when you start to think about it. It's very straightforward. It's just functions that calls themselves. If we take an example here, so we have a function called power here. So it returns a float, and it takes an argument x and some unsigned integer here called exp. This is the exponent. And then it has an if statement here. So it says that if exponent is equal to 0, then it will return 1. Otherwise, if it's different from 0, it will return x, and then multiplied by, then it will call itself again. So it will call pow with the same x, but it will decrease the exponent with 1. Okay, so if we have a main function here, and we would like to compute 10 to the power of 5 and store that in variable p. Yeah, so I think we take, okay. We were talking about a way to compute x raised to exp. So, for example, if you wanted to compute 10 to the power of 5, so how can we do that? And we can do that in different ways. And one way to do it is to have a function called pow that is defined recursively. So it will have a base case, and it will have a recursive part. So the base case is when this recursion will terminate. So that's the obvious case. So if you send in x raised to 0, it will, no matter what x is, the return value will be 1, right? So anything raised to 0 will be 1. Okay. And if we would like to compute x raised to 5, for example, we could think about this as x times x raised to 4, right? And then we can say x raised to 4 is x times x raised to 3. X raised to 3 is x. Oh, sorry. Like this, right? So this is the base case. It will return 1. And then x raised to 1 is x times x raised to 0. So that's what we get in this part. So if we now try to see here, we have x is 5 here, raised to 0, what will happen? And x raised to 1. So, so if we look at this program, and now we look at the stack. We talked about the stack on the last lecture. And it's one part of the memory where you can add element on top of the stack. You can read element on top of the stack and can write new values, and you can remove elements from the top of the stack. So in this case, what will happen is that here you will have a variable declared inside the function main, and it will have two arguments, argc and argv. So, and here they are put on the stack in this order. So p will be put as a variable that will be put on the top of the stack, and then argv and argc will then be put on top of this stack. And if we now try to call another function with the function pow with the two arguments 5 and 1, what we will then do is to put these two on top of the stack. Okay, so this first we put the last argument here, so 1, and then we put the first argument, that is 5. Okay, and we will always have a pointer that points to the top of the stack. So now we will start to execute the code of this function. Yeah. So the first time this function is called, x and exp will be 5 and 1, right? So now this, since exp is not equal to 1, or sorry, since exp is equal to 1 and not 0, so this will be false. So we will go down and execute this part instead. Okay, what we will now do is that we will multiply x with something where we call the function again with the same x but with the exponent decreased by 1. So now we will put x and exp on the stack again, but this time x will be the same, but the exponent will now be decreased by 1, so it will be 0. Right? So we will then execute the function again, and now we will, when we now evaluate x and exp, we will use the values that are on top of the stack, and it will be 5 and 0. Right? So at this point, this will be true, right? And then we will return 1. Okay, so and to return 1, we will now, as you see here, so since when we return from this function, x and exp will go out of the scope, and now we will instead put the return value on top of the stack. So we will return 1.0 here. And now we will take this, so execute in the first instance of this power function. So this will return 1, and then we will multiply by x, which is 5. So now we return 5 and remove the two variables that were on top of the stack. Okay, and now we will return back to the main function here. So then we can assign p the value 5. So this is basically the only thing you need to understand to get what recursion is. So if you know how the arguments are put on top of the stack when you call a function, then it's no difference between calling the same function again or calling some other function. You always put arguments on the top of the stack and then you return. Put the return value then also on top of the stack, and it grows and decreases in size like that. Okay. Yeah, so this is a nice way to understand how functions call each other. Okay. Of course, there is a problem with the stack, because when you have the stack, you need to set aside a certain amount of memory, and you don't really know in this case how many times will I call the pow function, right? That depends on the exponent, right? So if you give it really large exponent, then you will call it a lot of times, and then the stack will grow, right? So you have the stack will always be of finite size. So you might run out of stack space if you send in too large arguments. So in some cases, it could be better to rewrite it in some other form. So taking the same example again, we could do it without having the recursion at all. So we can, for example, rewrite the power function with a while loop instead. So, for example, here if we get x and x like before, we declare an integer variable I, and then we get some initial result, initialize that to 1, and then while I, this variable, is less than exponent, we take the result is equal to the result times x, and then we increase I by 1, right? So then we will do this until I is no longer less than x. So we will so when I will be equal to x, then we will not execute that, and instead we will return the result. So it will do exactly the same thing, but it's just written in a different way, where you don't have the recursion. Yeah, and the interpretation of this while loop is like you can do it with the if statement. So you have if, the condition, and then you have the statements, and then go at the end here, go to loop. Go back here, so it's a jump. It's not very nice to write it in this way, so it's much more readable if you put it in this form instead. Okay, so we saw two different ways to compute the same function with and without recursion. And some problems are very naturally formulated as recursive problems, but as I said, the drawback is then that you might outgrow the stack size. Yeah, so we saw the while loop, and that could be rewritten or be expressed as a if statement. But in C and in Java as well, for those that have programmed it, it's quite convenient if you have work with arrays, for example, vectors, to write it to have a for loop instead. So if you're gonna, if you have, for example, an array and you would like to do something on every element in the array, you typically use a for loop. So what you do is that you initialize some value, some variable here. So in this case, you initialize I to 0. And then you have a condition here. So as long as I is less than the exponent, then you will execute this. And then when you have done that, you will increase I by 1. So it's just the same thing as what we wrote with the while loop here. So this is also a non-recursive solution, so it doesn't need. I mean, in this case, the only thing that will be on the stack is x and exp, and then the result and I variables. But you will only have one instance of those. Okay. So what we saw now is that all of the variables that we have declared here are defined inside the scope. And last time we started to talk about addresses to memory as well. So I think we go to this. So let's say we have something like this. So if we would like now to declare a variable p here, that is, and then we initialize it to 2, and then we would like to compute 2 raised to 5, which would be 32, right? And then assign it p to be equal to this. So if you write this program and use the implementation as before, p will be 32, right? Because we assigned it here. But now look at this function. So it has no assignment here. It just calls a function with p as an argument. And if you now wanted p to be equal to 32 here, would that be the case? If we just called pow, p, and 5.
If you send the pointer, then...
Yeah. But as it is done here, right? So we send... So in this case, remember how it was executed. So x was put on top of the stack, right? And then when we return back, x will be removed from the stack and just the return result will be on top of the stack. So yeah. So in this case, with the normal implementation of power, p will not be changed after here, right? So let's say we did it like that. So we had this implementation of the assign, and then at the end we assigned x to be equal to the result, right? So we go look at this, what happens on the stack here. Yeah. So x will then have the value 32 when we return, but when we return back from this function, these variables here that were put on the top of the stack will be decreased, right? So they will no longer be changed. So p will be as it was before, 2. So the answer is no, and it depends on the stack. And a reason for this is that in C, all arguments are passed as values. So if we pass an argument, it will copy the value and put on top of the stack. So if you now wanted to get the behavior we described before, that P should change, what we need to do is what you suggested. We need not to send the value, but the address to the value instead. So how can we do that? So we go back to what we did last lecture. So thinking about the memory architecture. So remember that we have variables. They are just stored at some at some address location inside the memory. So let's say we could, for example, take the variable y in this case. So it was stored at address 5. So if we send in the variable, then we will get the address back, right? So this is not how we write it in C, but in principle. So we think that we had these functions. So we send in a value and we get the address to that value, right? And that we have, on the other hand, that we have the same or the opposite thing. So we could go into some address, send in some address, and we could get the value stored at that address. So call that function the memory at. So then we could do things like that. Okay, so then it would be possible to have a function that not got the value of P, but got the address instead sent in. And we can copy the address. That's not the problem. And then we change. So since P was the address, now we look at what is the value stored at the address P, and we increase it, or in this case we decrease it by 32, right? So if we have an example like this, we declare a variable y equal to 101, and then we call a function f, it's defined here, and now we send in not y, but the address of y, so which in this case will be 5, right? We let f execute, and now we try to print out the value of y. Since we sent the address and we changed the value pointed to by the address here, if we now print out y here, it will have a new value, right? So we could change the value of y without returning it back from the function. So inside the function can now change all the values of the variables described outside here if we send in the address to those variables. And this is something called pointers in C. So this is another, it's a very, it allows you to write programs in a nice way, because you can yourself decide on if you copy the value or you have the address to the value and so forth. So it gives you a lot of power, but it's also easy to screw up, especially if you're not experienced in writing C. But last time we talked about the ampersand and this star, and basically the ampersand means what we wrote here, address of. So if we put the ampersand before a value, or for the ampersand before a variable, then we will get the address to that variable. And in the same way, if we have an address and we put an ampersand before the variable containing an address, then we will get the value at that address. So ampersand is called the reference operator, and star will be the dereference operator. So you don't actually write it like what we did on the previous slide, but instead you write it in this way. So P here will be a pointer to or P will be interpreted here as an address to a character, to a location where a character is stored. So in this case, you will, since P is an address, so you go to the value by putting the star in front. So now you have the value stored at address P and decrease it by 32, and then you store it back to the same location. So what you can do now, if you would like y to change, is that you declare the variable y, like here, and then you send the address to y by putting the ampersand before. So now it's not sending the value of y, but the address where y is stored. And then inside the function it will change the value. So if you print out y below here, it will now be, in this case, if it was 101, it will be decreased by 32. As defined here, and then it will print it out, it will be 69. Okay, so when you then we look into all the code for the crazy fly, you will see a lot of these ampersand and stars. So it's important to know what they mean. And it might be a little bit tricky, but if you just remember that is addresses, so reference and the dereference operators. So you go take an address and get the value, or take a value and get an address. So then it's really not that strange any longer. So this I think is quite important here to understand. So especially those of you who have not seen this before. So yeah, please give me questions. Yeah.
Is an address a character then? So when we use when we want to input to a function an address, do we have to say it's a character star? Then the name.
Exactly, yeah. Because if you declared it as without the star here, then it will be interpreted just as a value, as a character, right? Now you would like, and remember on the last lecture we had a difference between the data types and the address types. So they can be of different size as well. So here you say that P is a variable that contains an address pointing to a character.
If the address is pointing to an integer, would it be int?
Exactly, yeah.
Okay.
Mm?
Okay, so 101 then is a character.
Yes.
Okay.
And then you get the address by putting the ampersand before. So, yeah, whatever address it might be, then the address will be put on top of the stack, and then it will put into the function, and then it will be, the address will be read, and then you dereference the address to get the value. So please interrupt me and ask questions here. I know that there might be many questions here. This is the first time you see it. It's can be a little bit tricky to get the hang of it. But really just think about the memory just as a big array with different addresses and values. So if you start to think in that way, it's not that complicated. And of course, a reason for not sending the variables directly, but instead sending the address of the variables, is if you have really large variables. Let's say you have large matrices. So then you will put the matrix on top of the stack. That will take a lot of time to copy it. And you will have to represent the same matrix twice. So then it can be much more faster to just put an address to where the matrix is stored on top of the stack instead. And another nice thing with pointers is that you can have memory allocated dynamically for you. Let's say you're going to implement a linked list, so a list storing an arbitrary number of elements, and you don't know beforehand how many elements there will be, right? So in this case, you could try to allocate an array of a really, really large size that you think should be sufficient, right? But it might still not be sufficient if there are more objects than what you anticipated, so then your program will crash. Or if it would be big enough, but then you have allocated the memory inside the computer and you have not used it properly, right? So because you have too large array, right? So instead you can create, for example, a linked list where you add a new element. Each time you encounter a new element, you will allocate some memory location dynamically and extend the list with a new object. So we will come back to those kind of things, but you can really use the memory in a very efficient way in this by having these pointers. You can also use pointers to refer to functions. So something else that we will see soon. So since a pointer is a reference to some address in memory, you can write programs that refer to addresses that doesn't really exist, that you don't own. And then you can your program can crash. So typically this is called segmentation faults if you try to reference memory that you don't own. Or you can have really strange bugs in your program. For example, you can try to refer to memory that has not been initialized and so forth. So you can really mess up when you work with pointers, so you have to be careful. So this is an example here. So what will happen now? You have a function here called getPointer. So it will return an address to a character. And inside this function, you declare x as a character, initialize it to 0. So it will be put on top of the stack here. And then you return the address to x. And let's say now you call this function getPointer and store in a pointer variable in this scope, and then you take that address, go into the value and assign it to 12. Is this a problem or not? And yeah, it is a problem, but why is it a problem?
X is local.
Yeah, so x is put on top of the stack, right? And of course you can get address to x, but something else. If you call some other function here, new values might be put on top of the stack. So it might be reused for some other purposes. So so you might have really strange problems. So this might or might not work, depending on what happens. But if we just look at what happens here, we create pointer, and then on top of it we created x, which was declared here inside this function. And then, let's say that x was now stored at address 101. So we will return 101. And now this will be, the stack will be decreased by this element. So it's no longer in scope. So pointer now points to, or PTR points to a location that is no longer in use and might be reused next time for another function call. So this is can be, if you write programs like this, you can very easily start to have bugs. So it's important to understand the concept of the stack and the scope of variables, and when it's okay to dereference pointers or not. Yeah. So for example, if some other function is called afterwards here, then that value will be put on top of the stack if that function has local variables, and it will be overwritten.
Is that a pointer option in MATLAB?
Sorry?
Can we use pointers in MATLAB? Do they exist in MATLAB?
I don't, not to my knowledge at least.
I researched for that and I didn't find anything, but maybe you know.
Yeah, so not pointers in this sense at least. So in Java, for example, you have something that are similar to pointers, but are a little bit different. So they are called references in Java. So in Java, you can dynamically create objects. So if you write x is equal to new, and then you send in some type, then you will get a reference to an object. So which essentially is the address of that object. But it is a little bit more, because in Java you will get help with maintaining the memory. So for example, if the variable goes out of scope, then Java has something called a garbage collector that will return the value to the or the memory to the operating system. But in C, that doesn't happen automatically. Instead, you need to explicitly return the value to the operating system. To my best knowledge, at least, if you need to do something like that in C, I mean, in C, you can have S functions, and in S function you can call C code, and then you can do these kind of things. So it's sort of possible. But it's not really something you have by default in MATLAB. So you should not worry about these things. Yes?
Is this an invalid declaration or a logic error? Because the pointer declaration is still fine, right?
Yes?
The pointer PTR.
So I think in this case, if you run this in the compiler, the compiler will not complain. So it is, and it might or it might not work, depending on what happens. So for example, if this other function is doing changes to the stack, then if you try to access the pointer afterwards here, it might have a completely different value. But if it doesn't, it might have the same value for some time until someone else messes with the stack. So, yeah, was that the answer to your question?
Yeah, I will follow up to that.
Yeah?
So can pointers be used as a good way to access local variables, like say x, which is the scope of which is only in one function? From another function, can I use pointers to access that?
So if you would like to have functions that sort of, so let's take you have this as an example where you have a big matrix that you would like to do changes to. So what you typically do is that you allocate that memory outside somewhere before you start to call these functions, and then you send the address to that matrix, and then you do changes. But what you should not do is to have the matrix declared or declared like that, so it's put on the stack, because then as soon as this function returns out, then it will no longer exist. But what is possible to do is to allocate the memory inside the function, not on the stack, but on the heap. And then there are different commands for doing that. So there are, which we will discuss later, malloc, that will give you some arbitrary piece of memory that is not on the stack, and that memory you can refer to also after you have returned from the function. Other questions? Yeah, so, and then remember every variable has a type. And you can also, in C, make your own types. So I think it's best explained by an example here. So for example, if you would like to create a type called myStruct, so you write like that, struct, and then you give it a name, and then you have this curly braces, and then inside this you will have a counter of type integer. You will have some other variable called average of type float, and you will have a timestamp that in turn is referring to another struct called timeval. So so let's say now you have a variable x of type myStruct. Then you can refer to the individual fields within that struct with a dot notation. So I think this is similar to what you've seen in Java. So you can, in this case, x.counter is equal to 1. You can do computations on it. So you can have variables of a certain struct that you have defined, and you can of course also have pointers to structs. So let's say x is now a variable of type myStruct. Then you, by having this ampersand, you will get the address to that struct, and now you can create a new type called pointer that is the address of a myStruct type. And now you have a different notation here, because if pointer is the address, then you will use a minus sign or hyphen and greater than sign to dereference, to like to change the counter variable. So then you don't use the dot notation here. So if x was of the variable myStruct, then you can use the dot notation. But if you have the address to a myStruct, then you have to use this notation instead. Or there is an alternative that you dereference the pointer was the address, and then you dereference it with the star notation, because now you will get the value, and then you can use the dot notation. So it's similar. Okay. And then something else that is really important to know about R in C for you specifically is arrays. So we talked a little bit about it. So let's say x, in this case you can say that x is an array with 5 elements, where each element is of type character, and then you can set the initial values like this. So you have the curly braces, and then you enumerate the different values for each element. And what is important to know is that the first element in an array in C, as in Java, is 0 index. So you access T here by writing x0. So if it was test, then you can change the first element here from a small t to a capital T by writing like that. You can also, in this case, you can have x plus 3. So you can do arithmetics on the addresses. So you increase the addresses by look 3 addresses forward and get the value at that position. So it will be the fourth element in this case. And something you will see if you start to look at control code written in C is something like this. These 4 loops. And a very common way to iterate over an array. For example, here you have an array of count elements, and count is declared here to be 10. So you have an array with 10 elements, and then you would like to do something on every element. So then for I is equal to 0, as long as I is less than count, you increase I by 1. And then you do what's inside here. So in this case, you would just print out the value of y at location I. So it will print out y0, y1, to 1, to y, in this case 9. So that will, so when I is equal to 9, this will be true and it will be printed out, but next time I will be 10 and then this one will be 4, so this will not be executed, and we will continue down here. So this loop will iterate from 0 to count -1. So this is the best way to iterate over all the elements in an array like that. Okay, so we have something more to say about dynamic memory. So we will do that when we meet on Thursday, and then we will dive into real-time operating systems and how to start to write parallel programs with concurrent threads. Okay, so good luck with the work, the project work.